Okay, like Rob said, my name is Mayank. I'm here with Facebook and with Renee, who's the human recruiter. So I'm going to give a quick tech talk, and then afterward, I'm happy to answer any questions either about the talk or about working with Facebook, and I'm sure Renee would be too. Unless there's anything you want to add, Rob, we can get started.
Can you explain that math?
We're going to taco. Yeah, I don't know what this is from. Thermodynamics, I think. Okay, so faster code for free. The title of the talk kind of gives it away, but basically, a lot of the time when we're writing code, we have recursive data structures like linked lists. And when we naively implement algorithms using recursive data structures, it's possible to accidentally implement a suboptimal algorithm because you either waste time recursing over part of the data structure over and over again, or you might evaluate more of it than you need to. And so I'm going to talk about a cool technique that you can use that will allow you to write those suboptimal algorithms, add one word to your code, and then have it magically become linear time instead of quadratic or whatever. And it's a bit of a spoiler, but the main idea here is I'm going to turn data into functions and then show you how expensive computations over data become constant time operations if you're just manipulating functions. So let's start with linked lists, one of our simplest recursive data structures. So if you know me, the talks I give for Michigan hackers always end up being in Haskell. Haskell is a functional programming language. And it's a really concise one for representing ideas in code, and so that's why I like to use it. However, this is not a Haskell talk, so I will explain the bits of Haskell syntax that are relevant, but you don't need to know how to write Haskell in order to understand the talk. So up here we have how we normally represent linked lists in a functional programming language. A list of some element type A is either nil, an empty list, or we get it by consting an A, the head of our list, to the tail, the rest of our list. So here's a couple examples of linked lists, right? If we just have nil, this corresponds to the empty list. If we take a nil, an empty list, and we const 0 to it, then that's the same as prepending 0, where we get singles unless we just do 0 in it. And we can do this recursively, right? We start with an empty list, we put a C at the front of that, a B at the front of that, and then an A at the front of that. And now we have the list A, B, C. So this is similar to how linked lists look in a language like C, for example, only we don't really have an explicit next pointer that I'm manipulating. The way you can think about this is if you have nil, it's like having an empty root node for your linked list. And a const, the first argument it takes, that A, that's the value at that node. And then the list A, which you pass to const, is the rest of the list, your tail of your list. That's what your next pointer is pointing to. Haskell has a slightly shorter syntax for linked lists, which I'm going to use, and that's this nice bracket syntax. Instead of nil, we just have this empty list, and instead of that big word const, we just put a colon. And we get the same list on the right side. So now let's work with linked lists. A common operation that you would do on a container is to join two of those containers together, right? Concatenate them. So this is what it looks like if you write that out in Haskell. This plus plus operator, I'm going to let that be your concatenation operator. And if we have an empty list on the left side and some other list on the right-hand side, then we just get the right-hand side list back out. However, if our left list is non-empty, that means it has a head, a first element, and a tail, the rest of the list, then we can recursively compute that concatenation by joining the tail to the right list and then prepending that first element. So translated into imperative code, this corresponds to starting at the root node of your left-hand list, traversing it all the way to the end, and then updating that final next pointer to point to your right-hand list. So, an exercise for everyone. What are the performance characteristics of this?
Traverse the list.
Right. Which list?
Your entire list.
Close. The first list, right. So in order to append two linked lists together, whether you want to think about it functionally or in terms of C++, in order to do that, you need to access the final next pointer in your left-hand list. And in order to get there, you need to get to the last node, which means you need to traverse your entire left-hand list. So this is important, because if we have a bunch of lists that we want to concatenate together, we can do them in a few different orders, right? We can start concatenating from the right side, or we can do it from the left side. So if we have a bunch of appends that we want to perform, and we start grouping them from the left, how does that perform? Feel free to just spitball. I'm not going to judge.
The length of the first three lists.
Sorry, what was that?
The length of the first three lists.
The length of the first three lists. So that's actually pretty close. In fact, that's what we would get if we group them from the right-hand side. However, because we're grouping from the left, it's actually worse. So we can just step through it in order, right? Doing this first concatenation, we already said to do a single concatenation operation. It's the cost of whatever list is on the left. So to do this first one, we have to traverse this linked list. So we have a total cost of A. Now we perform this concatenation. The total cost of doing this one is everything that's on the left side. So that's another A plus B. To do this concatenation, it's another A plus B plus C. So our total cost here is 3A plus 2B plus C, which is a lot worse than it needs to be, right? And again, the reason for that is to do this concatenation, we traverse this list and update our final next pointer. But then to do this concatenation, we start over from the beginning and traverse all of this to update the last pointer. And then we traverse all three of these to update the last pointer. So we very quickly hit basically quadratic complexity because we're retraversing parts of our code unnecessarily. And so here's that happening in action, right? So here's an example concatenation. We have 1, 2, and we have 3, 4, 5. So if we break our left-hand list down into each of the elements, the first thing that we do is walk past the 1, and then recursively append the 2 with the 3, 4, 5. In order to do that, we recursively walk past the 2 to do our concatenation. We already know how to add a linked list to something, you don't do anything. And then we have our final list. So we had to walk 2 steps, right? We had to walk past 2 elements in the left-hand list. So here's an example of how that can go really badly. So let's say we want to reverse a list, right? Reversing an empty list, you just get an empty list. And if you want to reverse a list that's made up of your first element and the rest of your list, you can reverse the rest of your list, the tail. And then at the end of it, you can reattach the head. So the question is, how does this perform? Oops. How many appends do you have to do in order to do this? Sorry, I heard someone say something?
Size of the list.
Right, size of the list. And what's the average cost of each of those appends?
N over 2 average.
Right, so big O of n, right? The length of whatever's on the left-hand side. And so if you multiply those out, that's quadratic complexity again, right? For something that should be a linear time algorithm. And here's an example of that. If we want to reverse a list of size 3, we can go through our recursive definition of reverse. But now the thing is, because of the recursive definition, if you remember, the recursion was on the left side of these concatenations, we start grouping these on the left. And so now we see that total cost quickly build up, right? To do the cost of this first append, that's a cost of 0 for walking the empty list. There's a cost of 1 to join these 2 lists together. And then there's another cost of 2 to join these 2 lists together, because we had to traverse this 3 more than once. And if this were to be a list of length 4, then our total cost would jump up to 6, then to 10, then to 15, so it grows quadratically. So I've kind of waffled for a bit about linked lists and functional languages, but the summary is basically what you kind of already know from classes in C++, right? If you operate at the root node at the head of a list, you get fast operations. Traversing a list from the head to the tail is fast if you need to see all of your elements. But just about everything else you do with a linked list is slow. If you operate at a given node in your linked list, or at the end of the list, you need to repeatedly traverse to get up to that node. So this is kind of what we expect from the STL, for example, right? Standard forward list, or what you learned in EX280, EX281. So the question is, how can we improve on this without compromising how we write our algorithms? So faster lists. We're going to use a concept called difference lists. And the idea is, instead of representing our lists as raw data, we're going to convert them into functions. And then, instead of appending lists and having to retraverse them, we'll just represent that as function composition. So, more Haskell, which you don't actually have. Oops. A difference list is going to be a function that takes a list and gives us a list back. We're going to turn our data into functions. So, given data, given a list of A's, how do we convert it into a difference list? So, a representation of a list is going to be the function which prepends our list to whatever list we give it. And in order to get our list back out, we're going to apply a function to an empty list. So, as an exercise, I said, how do these perform? There's really no work happening here, so these are actually constant time. So a couple of questions. What happens if we try to represent the empty list? Well, we get the function that prepends the empty list, so we get the function that does nothing, the identity function. And if we have the identity function, which I spell id, what kind of list do we get back out of it? Well, here, if you apply the identity function to an empty list, you get an empty list back out. So those two functions kind of convert back and forth with each other. If you perform one, then the other, then you get back to where you started. And so the important thing to understand here is that if we have a list which is a concatenation of two smaller lists, and we want to represent that as a function, we can actually represent each of those as functions first, and then concatenate them. That dot, that period is like the function concatenation or composition operation from mathematics. So appending two lists just turns into function composition. If there's any functional programmers in the room, how does function composition perform? So that's a constant time operation. And so we can also rewrite our reverse function. Instead of producing actual lists, I'm going to implement it so that it produces a difference list, a function. And then to get the actual reversal of a list back out, we will convert it to a function first and then convert that function to a list. And so this is actually going to be linear performance. But me talking about a PowerPoint is not as much fun as a code demo, which is what I really want to get to. So, let me go to the folder for this. Where's my cursor? Oh, there we go. All right. So I'm going to write some code in Haskell. And all I'm doing here is declaring a new file, and I'm going to hide some definitions that are normally defined for us, so I can define these functions for myself. So our first definition is how to append to lists. If we have an empty list and we append it to some other list, we get the other list. And if we have a list that's made up of a head and a tail, we can recursively join the tail to the right side and then prepend the head. And then if we want to reverse a list, we can reverse the empty list to get an empty list. Or if we have a list that has something in it, we can reverse the tail of the list and then put the head of it afterward. So, oh boy, that's going to be kind of hard to read. Let me do that. So I'm going to load up an interpreter. And we can actually, in the interpreter, look at how this performs. So let's say I reverse a list of 5,000 elements. Well, that's kind of ugly. If I get the last element of a list of 5,000 elements, that took 1.32 seconds. It's 10,000. Now it's really cranking through it. 5.73 seconds, and I don't even want to see what's going to happen with 20,000, but it's going to be kind of long. And it's actually going through a lot of memory to do this. Here it's going through 2 gigabytes of memory. Here it's going through 8.7 gigabytes of memory. This is not ideal. Okay, so while that turns through, let's see if we can do something better. So I'm going to define our difference list type. I'm going to define it a little different than was in the slides, but that's just because this makes it nicer to work with in actual code. And then I'll define our functions for converting a regular list into a difference list. Into a regular list. Yeah, so you can see reversing a list of 20,000 elements took 43 seconds, which is way too slow for me. And so with these definitions, we can define some useful lists, the empty list, for example. I can make a singleton list. And I can even write algorithms like our append function, which are slightly longer. So, given that we can do that, what does reversing look like now? So actually, I'm gonna copy this. So our function is gonna be called reverse prime because it's better. And instead of producing an empty list, I'm gonna produce nil, which is our new difference list. And instead of creating an actual list, I'm gonna create a singleton difference list, and that's all I changed. Right, the algorithm is still the same. And now we have a really fast version of reverse. Which we get by doing this weird reverse prime first, and then converting that into an actual list. Oh no, what have I done? Oh, of course, that's because I forgot to change this. We're gonna append. Okay, so now we can look at our performance again. So, remember that reversing a list of 10,000 elements took what, 5 seconds, 6 seconds? Eight seconds. All right, it's getting worse. If I change this to fast reverse instead, it does it instantly, and all of a sudden we're back into 4 to 5 megabytes. So, I don't know, maybe there's something to this weird stuff we're doing with functions, right? So, first of all, any questions so far? I'm sure there must be. Yes?
That was pretty awesome.
All right, I'll take it. Yeah. So, yeah.
Is this like applicable in like non-functional programming languages? I don't have much experience.
Yeah, so yes and no. This is kind of the question all functional programmers are hoping no one's going to ask them, right? Because no one actually writes functional code in the real world. Yeah, I'm going to say yes and no, right? The thing is, when you're working in an imperative language, right, and you can do things like manually walk a list yourself, you lose some of the concision. You actually have to like manipulate pointers and do all that ugly stuff yourself, right? I just get to say, hey, this is an equation, do it for me. But you get the advantage of being able to control state. So you can kind of, cache having already traversed part of the list and just keep going from there if you know that's what your algorithm will ultimately do. And so it's, from that perspective, it's not a problem that comes up outside of functional languages that much. But it's also kind of a good thing because if functions aren't first class in your language, you can't manipulate and pass them around like I'm doing. It's also a very tricky solution to implement. So yeah, on the one hand, this isn't going to magically improve your EEX 280 code, right? And I'm sorry for that. On the other hand, I hope it's convincing you that maybe there's more to the world than C++. Because I'm sure the university has not moved on from C++ since I left, right? Yeah, everyone knows that. Okay. Any other questions? I saw a couple other hands. No, everyone wants to know if this is useful, and I have to tell them no, it's not. Okay. So I said this is not a Haskell talk, and it's not. But for those that are curious about why this works, maybe from a mathematical point of view, there's a mathematical concept called a monoid. Any data structure is a monoid if you can create an empty version of it, and if you have a way to join two of them together, right? So lists are a monoid where the empty monoid, which we call mempty in Haskell, is the empty list, and where appending two monoids, or mappend, is just given by list concatenation. Similarly, difference lists form a monoid where the identity function is your empty difference list, and a function composition is how you append two of those together. And so there's actually a mathematical theorem from 1854 called Cayley's theorem. And basically all it tells us is that we knew how to do this for over 100 years and no one bothered. So I just want to throw that in there. Okay, so lists are kind of boring. Let's step up from lists. Lists are really just trees where you only have one branch, right? So let's look at trees, because those are way more interesting. So I'm going to define this new tree type. A tree can either be a leaf node, containing some value, or it can be a binary branching node which has a left subtree and a right subtree. And I'm not going to store any data at the non-leaf nodes, they're just going to be branches. So, one operation you can perform on a tree, I was going to say a cool operation, but I don't think anyone else thinks it's cool but me. You can take a tree, and at every leaf node, you can branch that leaf node out into a larger subtree. And this gives you a way of recursively building up trees. And I can define a function that does this for me. It takes in a tree, and it takes in a function that converts each leaf node to a bigger subtree. And then we can just apply that function at all the points in the tree. The code itself isn't that important. So monads. Trees form another mathematical structure called monads. This is also not a math talk, and so I'm not going to go into what monads are. But they give us a way of structuring compositions. And trees kind of represent a computation where a leaf node represents one that's already finished, you have an answer. And a branch node represents like a non-deterministic computation, right? You could go down either branch. So we can actually use that to build a tree, right? So I'm going to define a full tree to be this recursive definition. If I give it 0, it's going to give me a tree of depth 0, just a leaf, storing 0 at the node. And if I give it some larger value, it's going to give me a tree of depth n, and it's going to do that by recursively creating a tree of depth n minus 1, 1 less. And then it's going to take each leaf node, and it's going to expand it into 2 further nodes. So the question of how this performs, it's actually kind of similar to the issue with lists. This is also going to perform pretty badly. And so the hint here to figure out how badly this is going to perform is to realize how big a full tree is. So a full tree of depth n is a saturated binary tree, right? So that's 2 to the n elements. So this is going to take 2 to the n time to build this tree. And on one hand, that's bad, but on the other hand, the tree is that big, and so you can't really do better. However, we're going to start to see performance issues when we start traversing trees like this. So I can define this zigzag function, which basically traverses the tree by going left first, and right, and left, and right, and so on. And so if I'm just walking down one branch of a tree, how should that perform? Not how will it perform, how should that perform? Linear in what? In the depth, right? In the length of that branch. So zigzag of full tree n should be O of n. However, it turns out this is also going to perform quadratically. And that's because when we recursively build this tree, we actually do some of those repeated traversals that Play does in the list case, right? To build a full tree of depth n, you have to build up a full tree of depth n minus 1. But then to do all of that work of the leaves, to expand those leaves out, you have to retraverse the tree you just generated. And so instead of this being linear, it's going to be quadratic. And I can actually show a demo of that. Let's start a trees file. So here I'm going to define our trees module, where we can play around with some of those ideas. I'm going to hide a definition. Oops. Okay, that's just boilerplate. So let's define our tree type. So a tree of elements of type A is either going to be a list containing an A, or it's going to be a node containing 2 subtrees. And I can actually do this so that you can see what a tree looks like, and I can print it out. And so now we can do this substitution operation. We're going to take in a tree containing elements of type A, a transformation function that turns each leaf into a tree of type B, and then we'll get a larger tree with B-type elements back out. So if we substitute a leaf node into a function, then all we do is just apply the function. And if I substitute a node with a left subtree and a right subtree into a function, then I still expect to get a node back out, where we're going to recursively expand each of our subtrees. Okay. And I can define our functions to grow a tree. So grow n is going to be a branch. Times n plus 1. And now we can grow trees. Okay, so if we have a tree of depth 0, I'm just going to give you a leaf back out. And if we have a full tree of depth n, we're going to generate one of depth 1 smaller and substitute that into row. Okay, so what does that look like? Assuming this compiles. It compiles. So a full tree of depth 0 is just a leaf. A full tree of depth 1 is a node with a left leaf containing 0 and a right leaf containing 1. If we have a tree of depth 2, it has leaves containing 0, 1, 2, 3. Right, so we're going to get these saturated binary subtrees, and I know this is not the best format for reading them. but you can see that we're getting these trees of size 2 to the n, right? So now let's try traversing these. So I can define our little traversal function. So I'm going to first zig, that means go to the left, where you can't really go left on the leaf node. And if you have a branch, then take the left branch, but go to the right. You can't go right from the leaf node. Zig R. Okay. So let me reload that, and now we can see some of our performance characteristics. So if I zigzag a full tree of size 2500, okay, so in about a third of a second, it gave me a very large answer. It took about 700 megabytes. If we double the size of that tree, all right, now it's taking over a second and a half, and it's using 2.8 gigabytes. And if we have a tree of depth 10,000, and we traverse just one branch all the way to the bottom, it takes 6.5 seconds and 11 gigabytes. So this is quadratic complexity. This is not good. And actually, the fact that it's quadratic is only because we're using a lazy language, which is only evaluating the parts of the trees I asked for. But still, we'd like to be able to go faster than this. So how do we go faster? Well, we can actually do something similar to our difference list idea, but we can do it for trees. So the last thing I called a Dlist, so I'll call this a C tree because why not? I need a letter. So the same way we represented lists as functions, we're now going to represent trees as functions. And there's only really one function I've shown you so far, and that's that substitution function. So let's use that. So we'll take our new function tree type to be the type of that substitution function. And so in order to represent a tree as a C tree, we perform a substitution, or rather we get this partial function which will take in another tree and then just expand each of the leaf nodes into the tree we gave it. And in order to turn a C tree back into a regular tree, we'll do the same idea, except instead of applying it to an empty list, we'll apply it to an empty tree, i.e. just a leaf. And so the questions is, what do these do? And these actually do the same thing that happened in the list case. Converting an empty tree, just a leaf, to a function just gives you the identity function. And converting the identity function back to a tree just gives you the empty tree, just a leaf. And so in fact, these two operations allow us to convert between the tree form and the function form without losing any of our data. So this is the big picture. Earlier I mentioned that trees are a monad, which are a way we can represent computations. C tree is also a monad. I'm not going to talk about why it's a monad or how the monad implementation works. But the point is that we can use it to analogously represent computations. And then we can take our general tree interface and we can abstract it into another interface that both tree and C tree implement. We can use this interface to implement our functions for zigzagging and full tree, all the stuff that we've been using to build up trees so far. And then, because both tree and C tree implement this interface, all we need to do is flip a switch, and that'll let us go from the slow version to the fast version. So, what is this going to look like? So the first thing we need is to define what our tree-like interface looks like. The only thing that a tree-like interface needs to represent is how to build up a larger tree from two smaller subtrees. And that's what this node function is going to represent. It takes in two objects that implement this tree-like interface, and it's going to join them into a larger one. A leaf is going to be, we can define this utility function called leaf, which will just give us a basic building block of our tree, one of the leaf nodes. And then we can implement this interface on both tree and C tree. And then we can define new implementations of grow and full tree, which I'll call grow prime and full tree prime, which look exactly like our old implementations, only now we're using this generic interface with these node and these leaf functions for doing it. And then we can traverse it the same way we did before. So the question is, how does this perform? So we can actually find out. Let's go back to the code. All right. So the first thing that I'm going to do is say that our tree satisfies some interfaces. Let's see if I can type. Okay, so the reason I have to do this is that even though all we care about is that a tree is a monad, we still have to say how it satisfies some of these other interfaces. But fortunately, it's all boilerplate because I've already written all the actual code. Okay. So now we can do our faster tree. So let me define that type. And we can define functions for converting a tree to a C tree. If we have a tree called T, that's just okay. This will not compile, no. And that's because I need to install a language extension for this to work, but this is just Haskell that you don't need to worry about. And I also need to have the monad library available to me. Okay, so now this compiles. So again, I can make C trees a monad. I recommend you close your eyes for this. Okay, but yeah, the monad implementation is the only one that actually does any work, but believe it or not, it's a straightforward translation of the one I wrote earlier. The cool thing I'm going to show you later on is that you actually get all of this stuff for free because there's a library that makes it so you don't have to type any of this out. Where here x equals okay, there, that wasn't so bad, right? Okay, and now we can define this tree-like interface. That's what class means. It just means I'm defining an interface. And I want to have a node function that'll take two subtrees and it'll give me a tree back out. And then I can define a leaf function, which, given an element of type A, will give me some tree-like container that looks like a leaf. And then I can say that both tree and C tree satisfy this tree-like interface. tiles, that's always a good sign. And let me grab my functions from earlier. Okay, so now I'll translate these functions, so I'll turn them into grower prime and full tree prime. What do we need to change? Well, node is now lowercase, leaf is now lowercase, that leaf is now lowercase, this leaf is now lowercase. Instead of subs, I'll use that monad operator I defined before. Oops, reload. Okay, that reloads. All right, so I typed a lot of stuff. Let's see what the payoff was, right? So let's do our performance characteristics again. So to recap, if I zigzag a full tree of size 10,000, or depth 10,000, I should say, how long would this take us? All right, well that took us 7.5 seconds and it took 11 gigabytes of data, which is atrocious. However, now I've defined this fancy full tree prime, so this should be better. Okay, so maybe it's not better. All right, so basically the same thing. So I'm missing something. So remember earlier that I made it so that these are just implemented in terms of our Treelike interface. However, these are just giving us concrete trees back out. So I'm going to change this so that this gives us just something tree-like and not necessarily a tree. Okay, so now this has got to be faster. This is not faster. We still need to flip the switch. There's one more function which I'm going to call improve. And it's going to have this mysterious, like, convoluted type. But really, improve is just that abs function I defined before. So now, after building up our tree, I'm going to improve it first. And all of a sudden, it happens instantly, and we're back down to 23 megabytes of data. Any questions? Yeah.
What do you mean when you're saying like you're turning a tree into like a function? What does that
Yeah. So we're still in the code, right? So if we go up here, right? Actually, this type declaration is more complex than it needs to be. So let's look up here. All right. So our concrete tree type with our actual nodes and everything is this tree A, right? And so I have this other type, C tree, and here's the definition for that type. A C tree containing elements of type A is not actually a tree at all. It's a function. As input, that function takes another function whose input is this element type A, and whose output type is a tree containing elements of type B. And the result type of this C tree function is a tree containing elements of type B. So this is genuinely a function, right? Like in C you would, or C++, you would have to represent this as a function pointer or something. This is not actual data. However, because we're working in a functional programming language, we can manipulate it as data. And in fact, I can go back and forth between the data form of a tree, this concrete tree representation, and this functional representation of it. And these are the two functions that let us go back and forth. So if I go back to my definition of the substitution function, substitution actually takes two arguments. The first argument it takes is a tree with elements of type A, and the second argument it takes is a function. I promise you that's what that type signature says. It takes a function from A to tree of B. Here, I'm only giving it one argument. I'm giving it that first tree argument. The rest of it I haven't provided yet. And in fact, the rest of what it's expecting is exactly what this C tree type gives us. It's exactly the function type that C tree represents. Does that make it clear? A little bit. The list example is actually kind of instructive here, right? If I go back to the list example, here's how we convert a list to a function, right? We have this append function that takes two lists and puts them together. To represent a list as a function, I'm going to use that append function, but I'm only giving it the left argument. I'm saying the left-hand side is this list that you just gave me, and the right-hand side is still up to you. So this is still a function. It's expecting a list still. And then when it gets that other list, it'll produce the total list plus whatever you just gave it, right? Yeah, Haskell has a partial application, which maybe I should demonstrate. So, for example, we have your standard plus function. But I can say let f equal 2 plus, and now if I apply f to 3, I get the same thing. Yeah. Yes.
So for imperable language like Python, where we can treat a function as an object and do this kind of stuff.
If you're working in any language that lets you treat a function like an object, manipulate it like data, you should be able to implement something like this. Some languages will definitely make it harder than others. With C or C++, you can do basically anything with templates, but you're not going to enjoy any of it. Okay. Any other questions? Trees. Yeah.
Can you explain again, like why using functions makes it so much faster?
Sure. Let me go back. Did I go past it? Yeah. So in the example of lists, for example, right? Appending two lists, the cost of doing that is traversing the first list. Because you need to get to the last node. However, to append two of these functional representations, all you're doing is composing functions. And composing functions has no cost to it. There has to be some cost to doing this, right? Like, I'm not just generating lists for free, it is still linear time. And that linear cost happens here at this final stage where we convert a functional list back into a regular list. This is where all the final cost happens. Because this dlist function is basically waiting to prepend the entire list it's built up to this empty list. And the cost of doing that is linear in the size of whatever list has been built up here. And so you don't get away from that cost. But the point is that if you're building up intermediate lists using this concrete list data type, then you might end up with redundant costs from traversing parts of the list over and over again. But at no point do we actually use those intermediate lists. So if we can build up all of our intermediate values as functions and then finally flush all that data to a concrete list right at the end, then we save on all of that intermediate work. So that's the idea behind this. Yeah?
Does the composition of all those functions happen at runtime or compile time?
The composition will happen at runtime. Yeah, depending on what functional language you're using, the notion of how it executes, the mental model you have, if you're thinking of like C++ executing, is going to be a little different. Evaluation, think of it more as how you like simplify an expression in mathematics. Evaluation looks very much like that. Like, see how I was able to write this out just as a series of equations? The definition, oh boy, do we have erasers? No. Okay. Yeah, I'll just use this space. So to compose two functions, so f composed with g, we can define this actually as the function which, when you give it x, is going to be f applied to g of x, right? Like that's how function composition is defined in mathematics. That's how it's defined in Haskell. But there's no work to actually doing the composition. Like that's just a constant cost, right? All of the actual work is done when you apply these functions, when you finally provide that x. And that's what happens when we apply our Dlist to the empty list here. Okay, so that's how we get faster trees. So I'm a Haskellr, so I have to kind of take this in stride. We get a bad rap for using mathematical ideas, making everything really convoluted, and then we claim that our code is better than yours, and no one believes us, right? So you've heard about monads and monoids and functors and applicatives, and at this point, you're probably like, you said this was for free. This sounds like a lot of work to get faster algorithms. And yes, it's been a lot of work so far. So now I'm going to show you the final piece of the puzzle. We can make an even more general approach. So it's not really fetch your code for free. We're going to use the free monad for fetch your code. Oh. Okay. So we're going to represent our data types as the free monad of functor. You can define these general representation and like verification functions, which implement what mathematicians call the code density transformation. Then we can implement code in terms of not a Treelike interface, but a Treelike interface now. And then we can use this magical improve function I wrote before to get automatic speedups in our code. However, a library will do all of this for you. And so that's the really cool part of this talk. We don't actually need to do most of this work ourselves, and we don't need to care about most of the things I just talked about. Which I know everyone loves, right? So let's define a simple calculator. I'm going to show you how to define a language for implementing the calculator. Okay. There's some standard function definitions, and I want to define my own versions of them, so I'm just going to hide some of the standard definitions we've given. Okay. So, let's define a language. You don't get to do that every day. So, let's have our calculator do some operations. I'm going to implement a stack-based calculator. So we'll say one operation you can do is push a value. So here, by the way, so operation is this new data type. A is going to be the value type our calculator will work with. And next just means whatever the next step in our program is going to be. So we can push a value and then have it do something after that. We can have it pop a value, and then it'll maybe get a value, maybe it won't. So I'm going to use this nullable type called maybe. And then it'll need to do something with that value. We can flip the first two things on the stack and then do something after that. We can add the first two things on the stack and then do something after that. We can subtract the first two values. We can do some multiplication. Let's say we can divide, and I'll say we can do modulo. I think that's plenty. So earlier, I was writing all these functor applicative monad instances for myself. Well, it turns out there's only ever one way to implement a functor. So the compiler can do that for you. So now, I'm going to define these two types for us because they're useful later. Okay. So I'm going to load this in one compile. That's because I need to tell Haskell I'm using some language features. What else do I need? I need to import a library. Context. And compiles. Okay. So far all this is boilerplate, right? I've defined what operations I want us to support. I've used this free and monad free stuff, which this library provided for me to create these types. I don't really know what they do. And already I can start writing bits of our program. So, I can, for example, define a no-op. I can define a push function which will take a value. And I can define a pop. All right, this is already getting tiring. Suffice it to say that I could write functions that act like constructors for each of the operations I want to support. I don't really want to do that in the space of a code demo. But fortunately, the library actually lets me do that too. You can do code generation in Haskell. Oh, and that's because I need to import the code generation library. And all of this compiles. And so now I can already start writing programs. And now you might be asking, what does a program in this language look like? So I'll say program. So I'll say it's a program whose stack is going to contain ints. And I can do stuff like push 0, push 1, add, push 3, modulo. So for mostly boilerplate code, I somehow magically get this nice syntax for imperatively writing programs, which is already pretty exciting. But we can't really do anything with these yet because I haven't said how we should interpret programs. I built up a syntax tree for this new meta language we're defining, but I haven't said what to do with it. So we can define that. So I said we're going to be working with a stack-based calculator. So I'm going to define a utility function for manipulating our stack. If f is what we want to do to the first two things on the stack, then we'll do that. Otherwise, if we have a stack, we'll just get the stack back. And here I can define an interpreter. Can't see very well. All right, so if we want to interpret pushing something onto the stack, then we modify the stack by pushing that value to it. Interpret, and next. And then we tell it to interpret whatever's left. If we want to interpret popping a value, then we get what's currently in the stack. If the stack has something in it, then we get rid of the first thing on the stack, and we apply x to the thing we popped off. If we have nothing on the stack, then there's nothing to interpret. If we want to flip the first two things on the stack, can see if the stack has anything on it, and if so, we'll flip the first two things. Otherwise, we'll just return the stack as it was. And then we'll interpret the next thing in our list, in our program. And then the last ones are pretty straightforward. If we see an add instruction, we'll tell it to modify the stack using addition. If we see a subtraction, then we can modify the stack by subtracting the first two things. I can't see anything, right? If instead of subtraction we see multiply, then we'll multiply instead. And if we see division, then we can divide. And I think the last thing we had was modulo. Nope. Modulo. And that's because I need to add syntax. Is this indented too far, probably? Ah. Reload. Oh, that's because I don't know how to write Haskell. Reload. Alright. So now I can import the rest of the libraries I need to make this work. Control.moment.state. Alright, so now we have a language. We've separated it into a grammar, a syntax tree, and we have a separate interpreter for it. This is already like a really powerful pattern because I can define other interpreters. I could interpret this for doubles. I could implement a type checker. I could do a lot of different things. And then now that we have a way to interpret it, we can just execute it. So given a program, I can just say interpret it and execute it with the starting state of an empty list. All right, so we have our program defined up here. It pushes 0 and 1 onto the stack, it adds them, it pushes 3, and then it calls modulo. So if I say exec int program, executed 1. Let's see, does that make sense? Well, if you push 0 and 1, you add, and you have 1, and then 1 mod 3 is 1. All right, so that program's not super interesting. But we can do more complex programs. We have an entire language at our disposal, right? I could implement Fibonacci doing this. Fibonacci. So to implement a Fibonacci generator, we see if there's a value to use as input. If there was no input, then there's nothing to do. If we found an input of 1, then we can push 0 back. If we found 0, we'll put 0 back. If we found 1, we'll put 1 back. And if we found any other value, then we can push n minus 2, Fibonacci that, push n minus 1, Fibonacci that, and then add the result together. So instead of all of this, I could even say, like, give me the 24th Fibonacci number. What did I do? that's probably because I must have a type definition. Yep, I did. That's because I can't do that. I have to push 24 to the stack. And Fibonacci that. All right, so now, if I execute a program, you can see we now have Fibonacci number generation in our new language. So we can define subroutines, right? We can define subprograms and invoke them in a larger language, and then we can actually execute stuff. So at this point, we basically have a working implementation of Weeks 280 Project 5 in 80 lines of code, most of which is boilerplate. So that's pretty fun. However, this took kind of a while to execute, right? 2 seconds and 1.8 gigabytes of data to compute the fourth Fibonacci number. That's not great. So let's make use of this code density transformation thing I was talking about. So all I'll do is import that. And now, instead of executing our program, I'll improve it first. Right? I added one import and one word, and it executed in under a second and for less memory. Now, the thing is, Fibonacci as an algorithm, or at least a naive Fibonacci algorithm, already has poor performance characteristics, right? How does Fibonacci perform if you don't memorize? Anyone?
You have the previous thing.
Yeah.
I was gonna say
O of n. No, it's worse than that. It's exponential. Fibonacci numbers grow in proportion to the phi, the golden ratio raised to n. So that's actually exponential. It's like 1.618 to the n. So I can't get rid of all of the bad characteristics of our code, right? Some of it is part of the algorithm. But for example, I could show you, I could do a very simple algorithm. I could say 10,000 times push 1 onto the stack. And then I could say 9,999 times add the top 2 things, right? So this should sum up 10,000 copies of the number 1. So I should get 10,000. So this is not a very complex program. It's just a long one. And now we can see that this execution is really starting to slow down. This is that quadratic performance coming back to haunt us. I may have gotten overconfident with the value like 10,000. We'll see if this returns. Okay, so after 21.5 seconds and 21.8 gigs of data, I've computed the value 10,000. But I can just improve it. We can make the system for 21 megabytes. So this is kind of the final demo I wanted to show everyone. For very little coding, I implemented a language, implemented an interpreter for that language, and then basically for free, I let this library define these utility constructors that let me write this language using this do notation. And it gave me this free function that magically speeds up my code. So we started with lists and showed how to make them faster. We said, oh, lists are this mathematical idea called a monoid, and that's why we get to do it. And everyone was kind of like, whatever. And then I said, instead of lists, we have trees. And we can make trees faster because trees aren't just a monoid, they're a monad. And everyone's like, okay, whatever. But now, we have this very general notion of a free monad, an interpreter, and this code density transformation. And now I can just import libraries, implement my own language, and get really fast interpreters for it. So that's the magic of what code density can offer you. Any questions? All right. Well, that concludes my talk. So if you have any questions, feel free to come up to me and ask them afterward. I'm happy to talk about Facebook. I'm sure Renee's happy to talk about Facebook. So yeah, thank you for coming.
Yeah.